Alright, so I'll begin this podcast with just the last page of the last set of notes, which I forgot to go over. The real point of the fundamental theorem of calculus is that there's two conceptually different but generally equivalent ways of interpreting integration, as anti-differentiation and as a limit of approximating sums. Okay? Alright, so now we're going to look at the second definition, the second part of the fundamental theorem of calculus. Right, so the fundamental theorem of calculus is appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. And it gives the precise inverse relationship between the derivative and the integral. So, yeah, sorry about that. The antiderivative part of the FTC, if f is continuous on AB, then the derivative of our function f of t dt evaluated from a to x is going to equal f of x for every x in AB. Right? So that means that when we integrate, what we get back to is we get back to the original function. Right? And if we were to take the derivative, we'd get back to the integral. And we just go going back and forth. Okay, so the first part of the FTC deals with the, we should say the second part. So, like I said, the two parts, it varies who's called part 1 and part 2. But anyway, this part that we're dealing with is going to be dealing with finding the original function. All right, so the FTC deals with our equation here, where f is continuous and varies on a and b, and getting back to our function.
Wait, what does g of x represent? It's another function?
Because when you integrate, like the derivative is a function, so is the integral. Okay, so we're always dealing with a function.
So the integral.
We could call it a big F if you like.
Oh, okay, yeah, that would be better.
All right.
Like what usually shows up in Russell's grade book?
That was good.
All right, so here, observe that g depends only on x, which appears as the variable on the upper limit in the integral. If x is a fixed number, then when we integrate, we get a definite number. But if we let x vary, the number will also vary, and we'll define a function, which is dependent on this value here. And we'll look at some of that in this lesson. All right, so the concept of the indefinite integral using its formal definition. The integral, which is sometimes referred to as the antiderivative, is the inverse of the derivative for all values of x that are in the domain of the original function. In other words, given the derivative, the function of functions that have that derivative can be determined. Formally, this relationship can be defined by the fundamental theorem of calculus. The second part of the theorem states that if a function f of x is continuous over an interval and is differentiable, then the integral of the derivative, f of x, is the original function, big F of x. And the original function, big F of x, has a derivative, little f of x, for all values within the interval. So big F of x equals the integral f of x if and only if the derivative of f of x, so in other words, f prime of x, is little f of x.
We're not taking consideration of the constant, right?
No, exactly, not including the constant. So this definition states that the relationship, the original function equals the antiderivative with respect to x, if and only if the derivative of the function results in the given antiderivative. That's my writing. Therefore, the indefinite integral, or antiderivative, is the derivative of a family of functions which can differ at most by a constant value. So when we take the derivative, we lose the constants. So unless we're given some information, we're not going to be able to get back to the original function. But we can get the family of functions. Okay? They're just missing the constants. So when the indefinite integral is integrated, the family of functions that produce that integral is being determined. That is, given the derivative of the function, we should be able to find the original function for that derivative. By integrating the resulting function, it can be shown that differentiating and integrating are inverse processes. The result of integrating a function will be the function whose derivative is the function being integrated. So you can just go back and forth. Okay. When the integral is indefinite and no specific interval for the function is given, the result will be the family of functions whose derivative would produce the function that is the integral. When it's the definite integral, we get the area under the curve. However, there are many functions for which techniques to integrate do not exist. So that although an integral may exist, the fact that a function is continuous on an interval doesn't mean the techniques exist to integrate it. So we do have a couple ways of going around that, and it's one of our last lessons, which looks at trying to find a family of functions using the graphs of the derivative. See if we can figure it out from that. That's a little later on. Okay, so and actually this should say second fundamental theorem, but just know that we're going to the function. Now I'm coughing. So I'm going to end this tape and start here so I stop coughing.